Welcome everyone to today's Piper Serica podcast. First of all, a little bit about Piper Serica. We are a multi-asset management fund that manages different pools of capital. We primarily invest into fintech, deep tech sectors, which include space tech, semiconductor, advanced electronics, and AI. Technically, the companies which led IP to the growth stage. So we have Vijay and Amed, founder of SenseSemi today. Welcome,
Hi.
Amed, to the podcast.
Thank you.
Hi, Hardik.
Perfect. Uh, Good to see you again, guys. We'll start now. So, Vijay, you've spent decades building chips in some of the world's best semiconductor companies, and Namit, you also. So, before we get into the SenseSemi, what made you guys decide that this is the right time to build into the semiconductor company in India?
Yes, Hardik, of course, a lot of big companies out there. That has always been the case, when a semiconductor professional talks about it in India, for sure. So, primarily, a couple of things which really put me into why this has to be done or why semiconductors has to be done, right? So, primarily, in fact, 10 years back, I started my entrepreneurial journey, and then during that point of time, there were hardly any semiconductor things happening in India. But today, we see a different environment altogether. And one of the major thing where it led to this is definitely the COVID, right? So COVID, where we really had this shortage of chips, where people building the products did not had any chips coming in, right? And this was the case not only from the disease perspective, but this has continued into the geopolitical issues now, right? So everybody wants to have their own, system, and they don't want to allow others to come in. And this is exactly where it all boiled down to why this has to be brought in, as a semiconductor ecosystem which has to be developed, not for the sake of, luxury, but it's become a necessity now. And that is very important in today's world. And future is looking at more towards, connected devices and other things, and semiconductors plays an important role.
Makes sense. So, more on the geopolitics are changing, or the technology is changing.
Right, absolutely. So, definitely the geopolitical issues are taking a different tangent altogether. So each country wants to be independent in its own supply chain, right? And at the same time, the trust also matters to a lot of these product companies. And this is where India is looking very promising in terms of building the trust, building that bigger supply chain across the world.
Understood. So the technology is more towards the cloud or more on the edge side, edge AI side.
Right. See, I'll tell about my experience. In my 10 years of experience, or rather in 15 years of experience, when I built the first retinal chip, or rather I was architecting the retinal chip, that time I think one of the important feature was the compute was not there. So you still have to rely on the compute outside. That's the first case. And the second important case is, when there is no internet, what are the things? And this is something which is common across all countries, not only India, but across all the countries. And this is exactly where it boiled down to, look, what if we bring in the intelligence towards the edge? Correct. And that is one of the important reason why SenseSemi started off, building the edge AI to be brought in.
Understood. So, like nowadays, everyone talks about AI, cloud devices, factories. So, from a first principles, why does intelligence need move closer to the sensor? Like, if you can help us understand what exactly edge AI is in terms
All
of
right.
power, latency, bandwidth, how does it exactly it work?
See, one of the important thing is, yeah, you need to wait for seconds together if it is on the cloud, right? Now, all these sensors are becoming so minute. At the same time, I mean, you must have seen your own laptop, right? If it is, i3 processor or a Pentium
Right.
processor, the time it takes to load, it takes humongous amount of seconds, right? Now we are talking about milliseconds coming in, and the same tangent or the same shift is happening towards the sensor level, right? So bringing in the intelligence towards the sensor node itself, point number one, so which reduces the latency. Second important factor is definitely, we are talking about billions of devices eventually, right? And each one of them is trying to send the data back to the cloud. You're hogging the bandwidth just for sake of saying that, okay, look, this particular person has sugar, right? So that means that, for having to say that, something meaningful, you're going back to the cloud and coming back. That means it is not a viable solution. Why? Because you are not only burning the power, but you are also hogging the bandwidth. So that's point number two. And the third important point which I pressed upon is the the power side of things. So now if we are able to bring in the inferencing or the intelligence towards the edge, you are saving minute amount of power, but that minute from each device, if you're saving, that is a ocean of power which could be saved eventually.
Let me add a
Yeah.
couple of things here. One is, I mean, as you talked about, Vijay, this data explosion, because of that, there's a huge amount of power bandwidth. And you talked about latency. There's also the aspect of privacy. So, for example, in a healthcare application, or if I have a IoT camera-based solution in my house, the last thing I want is the data to go to the cloud, right? And I mean, we know that obviously everyone is going to provide security solutions for this, but the fact remains that if your data is going out, there's always the chance that it gets hacked. So there is no security better than the data never leaving, right? That is the ultimate security. And so a lot of places, a lot of IoT solutions where the customer would not want the data to be leaving their premises, whether it is at home, whether it is an industry, whether it is their health, their kind of healthcare related data, they'd want it to stay on the device. So if you want AI processing to happen on that, then you really want AI at the source, which means AI has to move to the edge and, to be more precise, to the actual leaf at the IoT device itself.
Understood. Understood. So, just out of curiosity, Namit and Vijay, in terms of whole semiconductor value chain, where exactly SenseSemi stands, and what are the possible use cases?
Sure. Maybe I can take that. So first and foremost, SenseSemi is building this SoC, which is an IoT device. It's a powerful MCU based solution, and it's with the AI capability. It's right at the leaf, which means right where the sensor is. Right. There could be different types of sensors over here. So it could be medical or healthcare related. For example, if you want remote patient monitoring capabilities, that could be one. It could be in industrial IoT. There is also a lot of use cases for this in things like toys or, for example, voice control devices. So actually, I mean, it's a pretty wide range of potential applications, but because we are integrating everything onto a single chip, it really can cater to multiple markets. But our focus area essentially is on industrial IoT and on healthcare.
Understood. And Namit, there are a lot of large incumbents are already there in the market. So, how exactly you are positioning the SenseSemi? And in terms of the technicalities, what sort of a nanometer chip you are building right now?
Sure. So what we are targeting is a very low power device. So obviously there are a whole host of devices that are available in the market, catering to different segments, different requirements. What we are starting off with, our first product, is very focused on very low power requirements. So battery operated devices essentially that can be used for years on a single battery. That's the basic idea. For that reason, what we are going for, or what we're targeting, is a 40 nanometer technology, specifically an ultra low power technology, so that for the most part, it's using extremely less power, and so it can operate on a battery easily. Uh, Apart from that, there are other reasons that also kind of lead to this choice. There's a choice, kind of a cost aspect. We want to make sure we are in the right price bracket. There is a performance that we also need to meet. So we can't, I mean, we could even go to older process technologies, but then we would not be able to meet the performance requirements. And then finally, we also want to make sure that we are able to bring in the right kind of data acquisition capabilities. A lot of those are analog in nature, and as it happens to be, analog devices don't really scale the way digital does when you go to smaller process technologies. So going to a smaller process technology for us would come at a big cost because it's more expensive, without really getting us the benefit that we are looking for, because a large part of our design is essentially analog.
Understood, understood. No, Vijay and Namit, even we also agree. And while we were doing our research, we also felt that the large incumbents right now are primarily building for the high computing processing powers, and these are specifically giving the way more features than the what exactly the smart energy meters, appliances, industrial IoT, basically where you need a low power kind of computing chips. So yeah, and we also feel ki there is a now the government policy framework are also building it up. Now DLI schemes have come up. Government has launched a 1 lakh crore of RDF fund. So now the public infrastructure is setting it up, and now the private capital will also go into that. And even from a public market side, there are a couple of companies like Keynes, the CG Power, who have got an approval for setting up their assembly testing plant. So basically, similarly, what happens in the EMS industry, like through the government support, we have built a couple of manufacturing ready, export ready product, and now with the help of DLIs and government support framework, we'll also basically build a whole semiconductor value chain through that. So perfect. You have also mentioned about the product called Sense NPU. What exactly that? And without going into the buzzwords, if you could help us understand and break down the Sense NPU chip.
Like we talked about, we are bringing AI compute at the chip, right, directly at the chip itself rather than sending it to the cloud. But there's a big difference in terms of what the requirements are on a chip like this versus what you want to do on the cloud. So the cloud, for example, to a huge extent is LLM, and what most of us are now getting used to, agentic AI. But that's not what we really want on these chips. What we want on these chips is the ability to be able to take a command, for example, the ability to take a signal like an ECG signal and be able to look at it and identify arrhythmia. So it's a very different kind of requirement with a very different power as well. Further, first of all, it's a lot less compute intensive than what we do on the cloud. But power is a huge, huge, huge concern over here because the whole point to a great extent is that we want battery powered. And the architectures that exist for the cloud are, I wouldn't say they don't care about power, but performance comes first and foremost, and power is a distant second. But for us, power is usually important. So since NPU, and I'm trying to keep it as kind of non-technical as possible, I'll try and break it down to three primary things that we are trying to do here. The first thing is that machine learning or AI, the actual computing, is a lot of math involved, and the math is basically a huge amount of matrix multiplication, just multiplication. Now, the reality is that digital designs work on binary math, and binary math really has very brute force solutions to multiplication. It's really not suited for multiplication. And so, what happens is to build a multiplier, you end up burning a lot of power, a lot of area. What we are doing is we are moving towards analog computing. And analog computing is not based on binary math, and in fact, literally using the kind of the physics of resistors and current, and so you can create a far more elegant, far more uh, power and area efficient solution with analog compute. So that's number one. Number two is what we call the von Neumann architecture, or kind of simply put, in most computing systems, you have memory and you have compute, and they tend to be apart from each other. And in machine learning or AI compute, the amount of data that goes back and forth is huge, much more than, for example, the old CPU requirements used to be. Um, so now, when memory is far away from the compute, what happens is A, you burn a lot of power just moving data from point A to point B, and two, your performance limitation doesn't come from the compute. It's not about how many cores or what you have there or what frequency. It becomes, can you push the data fast enough to the compute, right? So that becomes actually your limitation rather than the compute itself. So what we're doing is we're moving to what is called in-memory compute, which basically moves the memory right where the compute is, thereby reducing all of this movement of data from point A to point B. Now, obviously, it's not simple, and it comes with a lot of kind of complications. Otherwise, everyone would be doing it. But for us in the space that we are in, which is the edge compute, there is an advantage of doing it. Whereas if it were at the data center level, the disadvantages of doing it would outshine the advantages. But but our priorities are different, and hence we see a big benefit of doing this. And then finally comes the entire neuromorphic compute concept. So essentially, neuromorphic compute is nothing but a model of how our brain works. And it is the fact that the human brain is the most energy efficient computer that we are aware of, right? It is by far the most power efficient. So there's a lot of work that has gone into understanding how the human brain works, and essentially what it works kind of like is what we call spiking neural networks, and that's the model that we have created out of it. And essentially, at the heart of it, what it really, at the very basic level, what it means is that in our normal AI processing, what we're doing is this data coming in, we are just computing all of it, right? Whatever it is, we are computing on all of it, and then we're deciding, oh, it's nothing. Okay, it's nothing. This one, I don't have to do anything on this data. So we burn power continuously without necessarily having to needing to do so. Neuromorphic computing is based on what is called a spike. So it's basically got mechanisms built in the very architecture of it, where it can decide what is worth computing and what is not. So it knows what to ignore and not continue to burn power on that thing when it is not worth computing on. So it's a very different architecture, but it's a very energy efficient architecture. And that is, so that's another reason why we don't make this. So these are the three kind of components of what Sense NPU is.
Interesting. Interesting. So, Nand, there's a lot of hype around 5 nm chip, 3 nm, then 14 nm chip, and you have deliberately chosen 40 nm. Then eventually you will go to shorter nodes as well. So, what made you choose specifically 40 nm, and why there's a hype around 3 nm, 5 nm chips also?
Sure. So, it's what we call horses for courses, right? So, we are all talking about 3 nm, 2 nm, 5 nm because we are talking at looking at companies like Nvidia, Intel, AMD. These guys are building chips that are meant for the data center. So the few things to note about them. Number one, their chips are anywhere from 200 to 50 mm square to 600, 700, 800 mm square. Now, to the layman, 800 mm square is not a big number. I mean, this eraser is way larger than that. But the reality is that for a chip, that's a huge chip, right? And it's got tens of billions of transistors on it. Um, but it's 95% digital, right? And so for them, optimizing the size of the chip is the number one priority, right? So going to 2 nm means I can pack in more transistors into that chip, which means I can do more compute, which means I can offer more to the customer at the same price. So that is their driving factor. And they're ready to pay the big bucks for it, right? 2 nm, for example, is more than double the cost of 5 nm, right? But it's worth it for them, but because that's what their market requires. For our market, one, we are very analog heavy, we are RF heavy, which means that we are not getting the advantage of going down to smaller process technologies. In fact, going there actually makes life a lot more difficult because they are not really suited for analog design. And second thing is, for the market that we are at, the cost of the chips is dramatically different, right? We are trying to, like, not just us, but the entire market is trying to do $1, $2, maybe even 50 cents chips. And there's Nvidia trying to sell a $35,000 chip. Right. So naturally, their priority is totally different from our priority. And that's why something like 40 nanometer kind of works very well for us in terms of the power, in terms of the compute capability, in terms of the analog and RF design that goes onto it, while also keeping the price at the right point, right? So, yeah, as I said, it's nice to talk about 2 nanometer, 3 nanometer. I mean, we've also worked on smaller technologies before, so we have experience with it. But the point is, it's the wrong solution for this product.
Understood. So just a follow-up question on this. So now, so how's the supply chain to build these kind of a chips, 3 nm, 5 nm, or even the 40 nm chips? And whatever I could read, supply chain is quite concentrated towards a very few regions: Taiwan, China, US, Japan. So how should someone look at this also?
Primarily, the 3 nanometer or less than, let's assume 22 nanometer. So let's talk about 16, 12, and 8. 2 nanometer is far away. One thing is, definitely the reliability also matters. quite a lot when we go on to 2 nanometers and other things. The fabrication companies are struggling with that, not only on the fab but also on the assembly as well. But on the geopolitical issues as well, if we try to do it, one thing is China definitely doesn't have the lower end technologies. It does have the higher end technologies, like maybe 16 up to 16 or 22. But most of these technologies are being controlled by the Western world, right? And it is very difficult to innovate. Though India has started late, but we have started somewhere, right? But things have gone to 2 nanometer in 20 years, right? So that means we cannot get onto a fab which is 2 nanometers or 5 nanometers immediately. It takes a gradual process. And as I said, most of these technologies are controlled. It will be another difficult area where we need to pitch it in. So keeping all these things, keeping 28 or 40 holds very key for solving the local problems, right? Rather than being too generic or being too optimistic in saying that okay, we are going behind the performance to deliver that chip. And I totally agree with Namit, in terms of the analog and RF hungry, or the concentration of RF and analog designs. Definitely these technologies, lower end technologies like 22, 28, 40 holds very key into the geopolitical issues as well.
Understood. And we are also quite aware like how the PLI has taken up in India for upgrading our electronic manufacturing services, and a couple of companies have basically gotten benefit. And now recently, government has also announced a DLI scheme. So, do you think that DLI will be able to repeat the successibility of the PLI also? And
Absolutely, Hardik.
their
Yeah.
ecosystem in India?
Absolutely, Hardik, because why till now PLI has not kicked in into semiconductors chip per se, right? Designs per se, right? As I said, there are two things. One is fabless and fab. The fabs are being given PLI when they start now, packaging and testing the production version of the chips, right? And that is going to kick in much faster, right? But at the same time, these fabs or OSATs, when they come in, we still have to have enough fabless companies to kick in. And that's where government did a fantastic job in getting DLI 1.0, and we are a beneficiary of that as well. And it has taken step by step evolution as well. Now, as you read in the paper, there is DLI 2.0 also coming in. At the
Right.
same time, there is also ISM 2.0 coming in, right? So what
Right.
it means is, ISM will come in with more features for fab related stuff, right? More fabs could also arrive at it. Excuse me. But going forward, DLI has taken a good step to get the first 20-25 companies. DLI 2.0 will be more companies coming in. But unfortunately, PLI cannot kick in as as we speak now, right? Because there are no chips which are production worthy in this year. But going forward, maybe 27, 26 Q4, we could see more, at least one or two companies coming into the production version, and the SenseSemi could come in Q1 of 27. But that's when the PLI scheme kicks in, and these PLI schemes will also help. In fact, it could also add value for the existing EMS companies, because there could be policies coming in where the government mandates that if you're building a product, you need to use at least one Indian made chips, right? And that kicks in for not only the PLI, not only for the fabless, but also the product companies which are building in, right? So that holds very key, and that is the expected and well thought aspect from the government as well to kick in probably in this budget. Hopefully, we hear that coming out, or probably later in this year, this aspects will come in.
Understood. So, how's our capabilities in terms of assembly, testing, and packaging? Obviously, we know recently Tata has also announced to open up a plant in Dholera, and then Kane Semiconductor has also planning to build the semiconductor plant. So, how's our capabilities in terms of ATV?
See, primarily, India has taken that step to build in the OSATs first, right? That's where we could see Canes coming in and Tata coming in from the OSAT perspective. But at the same time, the fabs also have to come in, right? And India has taken a big leap with Tata's fab, which is going to come in Gujarat as well, which is more like a 28 nanometer. That's where, things will stabilize, because we also have to see not only from, a global perspective, but also from local perspective. So that has taken quite a bit aggressive step to build in the OSATs. And as we see, within a year's time, we are seeing Kane's kind of OSATs, OSAT companies are coming up with their first package chip as early as, this quarter, right? Now that will improve, or rather more companies will do their OSATs in this year. And I see a big shift in why not the global companies, global fabless companies should look at Indian OSATs to come in.
Makes sense. And I heard there's some partnership has also done with Micron.
Yes, Micron is a memory company, and Micron is setting up its OSAT as well as, to a certain level, fab, if I understand correctly, to build the memories locally from India to the world. And that's an important step which the global semiconductor is looking at India as a lucrative market to do it for future.
Understood. And as a design company, SenseSemi, what should be the key milestones to track for?
I would say there are 3 points, or probably four, but let me just explain. In the fabless semiconductor ecosystem, unless you have a chip, it is very difficult to say that you need to go to customers. But at the same time, we are fortunate to see that a lot of these OEMs and ODMs are being set up in India, and talking to customers have become more easy as compared to it was 5 years back, right? Most of the product companies, system integrators, are coming in India, setting up its operations, or setting up new product in their roadmap. So this has helped us to see that, look, either we can validate our idea, saying that, okay, we are building it and this is how it has to go. And that is where it has been acknowledged by most of the companies for most of the fabless ecosystem. Now, that is the first step which we have taken proactively, working with Kane's Technologies, working with customers, potential customers like inventors, potential medical devices companies. So now the next step which goes into is, how soon can we give certain prototyping to these potential customers to test it out, right? It could be a FPGA aspect, or it could be a eval board, where you think that it is a unique aspect which they can test it. So that is the first step which we have done it. The next important step in the fabless ecosystem is the validation of the ideas. One of the thing where it slightly becomes challenging for analog RF companies is because you can't do anything as a prototype on FPGA, and this is exactly where you need a test chip to be done, and this is exactly where we are doing it, right? So the semiconductor ecosystem would require at least 2 test chips and then go into production for the third one. And this is the typical execution cycle what a fabless semiconductor product company has to take.
Understood. Perfect, Amit and Vijay. So how do you see now the Indian ecosystem or the global semiconductor ecosystem to be scaled up in the next 5 to 10 years?
I would say that India is growing, and India is the place to be in at the right time, especially for semiconductors or deep tech, right? And if I have to talk about semiconductors, where we are going to see in next 5 years, or probably next 2-3 years, I think there are challenges as well, right? So there are those challenges have to be overcome, and we see a potential factor which drives India to the global network of semiconductors is the trust, which I totally believe, and the privacy, the security aspects, which also has to be brought onto the chips what India is developing in its innovation. And the fourth important point is the innovation itself, right? So yeah, we just have to grow in terms of innovation for the next future, be it quantum. How quantum integrates with semiconductors or the CMOS technology also has to be brought in. So these are the driving factors where I would see where India will play an important role. And the fifth important point is also the sheer consumption, right, of the of products are going to happen, will shift from Western world towards the Asian markets, what we see. And this is the right time to be there.
Understood. So we are entering into a more connected world, either in terms of edge devices or in terms of AI.
That's correct.
Absolutely, yes.
Perfect. Uh, Thanks, Vijay. Thanks, Amed, for your time. We are proud to partner with you on this journey and excited about what lies ahead. And we'll build a large semiconductor company.
Absolutely. Thanks, Hardik. Thanks, Piper Serica, for being there, supporting us. And I still feel that there has to be more deep tech investors coming, and they should look at semiconductors more proactively. And thanks to Piper being the backbone for this at SenseSemi.
And it's been great working with you from last 1.5 years, and then we build an investment over that period of time.
Yeah, absolutely.